Okay, so that is the day that I'm defending my thesis. That's the day. So everybody look at it. You can all look at it. So you're all invited that day, January 26th. This will be part of my thesis, this talk, but it's still, the presentation's a little bit rough, but this is the day, 26th. Which day is it? 26. 26. There's also a party that day. You're all invited to the party as well. Okay. Okay, let's start the slideshow then. Okay. 26. Okay. All right. So as Jan was mentioning, dragonflies and damselflies are pretty old. I think they're some of the oldest insect group that we have around. Someone can verify that for me, but I believe they're one of the oldest extant insect groups we have still existing, which totally goes against what Beatrice just said. You just forget everything she said. No, of course, but of course, these gigantic dragonflies we have here are much different than palm damselflies that Beatrice was talking about. And obviously no one sees something like this flying around anymore. But even as close as 150 million years ago, we all remember that time when we see quite a large size decrease. So this is important. You want to remember this pattern throughout the talk. And then today we have just sort of slightly smaller max body size. But this middle part is the one that I want you to remember. Okay. So here is a fossil history of the body size evolution of dragonflies and damselflies. In case anyone's seen my previous talk, this is not the same talk. These are just the first two slides. So if anybody's getting worried that they've seen this talk before, it's the different talk. Anyway, let's go through this talk. Let's go through these. Can we see this pointer? No, we don't have a pointer. Anyway, so we have these huge dragonflies and damselflies, bird-sized, 300 million years ago. And then we have, over here, we have 150 million years ago, slightly smaller, but still pretty large dragonflies, right, in this point. And then here we have this extinction event here, the last one that Beatrice mentioned 65 million years ago. Now we have our extant, very small, very constrained group of extant dragonflies and damselflies. Okay, so some of you might be thinking already, I know the answer to this, it's oxygen. It was oxygen, I read about this, it was oxygen. It's all oxygen. I'm done, I'm tuning out the rest of this talk. That explains everything. Well, it's interesting because here we have lower oxygen level in this 150 million year time span, but we have larger body size than we have today, even though the oxygen's slightly lower. Oh, so your oxygen theory is a little bit, it's not holding up so good either. And you might be thinking, okay, maybe it's not dragonflies and damselflies, but it's a general rule for insects, so they're probably it's just a one-off case. Well, you're also wrong about that. So here we have 10,000 fossils of all sorts of insects, and we see this is a general pattern. So I think we have all kinds of insects, beetles, moths, flies. The huge ones here so that largest one there is still a dragonfly. So, but anyway, we still have this problem if we look at all insects. So we probably need a general explanation for why things are smaller than they used to be. So one explanation that has been put forward is that something has arisen during this time, which is a lot of people believe that it's some sort of flying predators that have constrained body size since 150 million years ago. So that's one idea based off. So that's maybe why we have this constrained body size here later on. All right. So if we look at present day variation, so this is variation across the globe of all dragonflies. So we might think to ourselves, okay, what are the patterns of variation that we see today? And are there any environmental causes of these patterns that we see. So if we look at the dragonflies here, it's kind of hard to tell, but yellow would be your sort of slightly larger dragonfly. So this is the mean of the region. So it has a mean of all the species in that like polygon there. Then you can sort of see, you might be able to sort of tell that there's slightly more green as you move into lower latitudes. Like in South America and Africa, there's slightly more green. So you might be thinking, okay, there might be some sort of latitudinal gradient here. Okay, then if we look at Zygoptera, we see sort of the same kind of pattern. We see like green, this time green is like slightly larger because damselflies are smaller than dragonflies. So we see here again, we've got some green in North America, green in Europe, and then some yellow down, and then even some very small maybe in Australia there. Okay. So there might be some pattern here. So if we look at this statistically, first panel we have here, panel A, we see that if we look overall, dragonflies and damselflies, in temperate regions, the blue column, they are larger, all right? But we see the opposite pattern for damselflies than we do from dragonflies. So it seems here that maybe damselflies are actually larger in the temperate regions, looking at this first panel here. And then dragonflies larger in the temperate region, larger in colder regions. The blue is larger. But if we account for phylogeny, if we account for the fact that we might be measuring a lot of closely related species in the damselflies, we see that the pattern actually kind of disappears after we account for phylogeny. So we still see a slight larger in the temperate region, and also slightly larger in the temperate region for damselflies, and larger for dragonflies. So it seems like we've got a temperature effect here, that things are larger in colder regions. So then you might also be thinking to yourself, okay, I know the answer to that, just like I knew the answer to the other thing. It's Bergmann's rule, right? I got oxygen and I got Bergmann's rule. Well, that might be true. I mean, here we have a graph of moose body size in Sweden. I mean, moose and dragonflies are quite different, right? I mean, dragonflies don't have an endothermic way of generating heat, whereas moose definitely do. So that might be different. But if you're a very smart member of the audience, then you've already guessed, but I know a rule for insects, the temperature size rule. Wonder how many people knew the temperature size rule. Anyway, so if you grow insects, or if you raise insects in colder temperatures, they will get larger. So okay, the talk is over now then, right? We've figured everything out. See you guys January 26th. The talk is over. We figured it out. Again, we have the whole answer. Okay, well, that might be true. So just out of curiosity, let's look at the fossils now. Let's just look at the fossils and see if the pattern holds up through time. Well, if we look at our first series here, so here we have, Beatrice had a beautiful graph of the continents shifting around through space and time. That was a beautiful graph. So here we've taken into account all those movements, and we have taken the latitude from those, so this is called paleolatitude. So we take into account all those complex movements of the continents in the past. So here we see in the first panel, we see this negative relationship between body size and latitude in dragonflies in this first upper top panel. So this was 210 to 150 million years ago. So we have a negative relationship, which is the opposite of what we have today, right? Because previously we had a positive relationship. Dragonflies and damselflies were getting bigger as it got colder. Again, 150 million years ago to 80 million years ago, we also have a negative pattern. And then something strange happens here, 82 extant time period on the dragonfly lineage. It seems we have perhaps a reversal of the trend, right? So now we have suddenly, dragonflies are starting to get larger as we move into northern latitudes. Okay, that's surprising. And so damselflies have always kept, and then damselflies have always kept this same sort of negative relationship, and then maybe it has become shallower in the near present. Okay, so that's interesting, right? It has shifted. So maybe we have to explore this temperature size rule a little bit more. So some of you may have seen this graph before. So it's possible to infer past shifts of body size from a phylogeny and some present-day body size information. So here I've plotted the sort of reconstructed shifts, significant shifts in body size in this lineage. So we see this large one here you're probably noticing. So here we see a very large positive shift in body size for this damselfly here. And then we see the green also. We have a few positive shifts for dragonflies as well. So with these shifts, we can actually model how sort of the evolution of these shifts and also temperate range. So we plug this all into a phylogenetic comparative model. We get back this result. So one might be thinking, okay, if temperature is responsible for causing larger body size, then I should have migrated to Sweden at some point and then discovered that it was cold, right? And then evolved into a larger body size. So that's what our model should show. But our model actually shows the opposite. It shows that I started as a large dragonfly or damselfly in the tropics, and then I moved to Sweden and I stayed large. So it seems that there might be some filtering going on between temperate and tropical latitudes, that also only those lineages that have evolved a larger size have decided to migrate to the temperate region. So that might be partial explanation for our gradient that we see between temperate and tropical regions. Okay, so we can also fit another model where we look at, okay, so this is just looking in Europe because that's where most of the data is available. So if we try to fit a model of how temperature is affecting body size just in Europe, we can fit a series of models like this. So this is something called a phylogenetic path analysis. It's just like a regular path analysis, but it takes into account the non-independence between species. Okay, so our first model here is the best performing model. I don't know if you can see it, but it basically says that temperature has a negative effect on development time, and development time has a positive effect on your body size. So if you're developing longer, you have a larger body size. That makes sense. And if your temperature is lower, you are developing longer. That also makes sense. What's interesting to point out is that we don't see any direct effect of temperature on body size. So that's what you would expect if you had some structuring of the population or structuring of dragonflies and damselflies by species by temperature. So that temperature was deciding where you lived as a dragonfly or damselfly, then we would expect a direct effect of temperature, not this just indirect effect of temperature on development time. So this direct effect of temperature on development time does support our temperature size rule, but it doesn't really support a structuring of the population based on environmental temperature. How much time do I got? Okay. So here's just a map of temperature. This is like the dragonfly view of temperature. So this is what the temperature is according to what's available in terms of dragonfly distribution. So we see that temperature is not a big predictor of distributions in Europe, or not at least a direct effect. But if we map it all species, not using this phylopath analysis, so just looking at the direct effect of temperature on body size, we do see a negative effect of temperature. So as you would expect, given that we do have this latitudinal gradient, if it's lower temperature, we do have larger body size. But one surprising result from all this is that something I actually did not believe was true, and we can discuss this, but something that actually also has a negative effect is bird diversity. So that's a little bit strange, right? Why should bird diversity have a negative effect on your body size as a dragonfly and damselfly? It's very strange, right? So I have a couple ideas. So this even holds up if we include temperature in the model. If we include precipitation, it also has a negative effect, negative significant effect. If we include tree cover, a lot of, you can include, I think I included, yeah, I was basically trying to destroy this effect, like it seems spurious to me. Could still be spurious, right? But right now, as it holds, the models seem to be indicating that bird diversity has a strong negative effect on temperature, which seems to agree with what people have been saying about the fossil record, that perhaps birds are a major player in constraining our body sizes here in the modern day. Okay. See if I have any more caveats than that. Okay, so conclusions. Temperature has only had an indirect effect on body size distribution. So it's probably just coincidence, or not coincidence, but it's probably just like temperature is probably not the main driver of this latitudinal gradient. It's probably more likely maybe biotic factors, maybe dispersal or predation might be causing this gradient. And maybe birds are even occupying niches that larger dragonflies used to occupy in the tropical region. Okay, that's the end of this presentation. Thank you all for listening.
Okay, I would like to ask.
Okay, Ivers, yes.
To use my privilege.
Okay.
So, but do you think, like in insects, it's related also to puberty? So, if you have like development, you have later onset of puberty, and it's basically like once you start mating, you stop growing. Isn't there such a thing?
What do you mean for the larval development time? Or?
Yeah, you have like delayed development, then you have later onset of puberty, and that's why you're larger.
Yeah, so that could be the mechanism for this temperature size. That could be one such mechanism, and I think that's probably the mechanism. Yeah, yeah, for that, yeah.
Okay.
Okay, so thanks for an intriguing talk, really, in many ways. So I was just wondering, the last statement there makes me think about what dragonflies eat. Today, extant dragonflies typically are feeding on other insects, right? Mostly, as adults, right? Did the historical, the fossil dragonflies eat something else?
I do not think so, but they could have. I believe that they were also insectivores, so as far as I know.
Right, so there weren't any seed-eating dragonflies?
No, I don't think so. No.
So birds now fill, a very tiny niche space, right?
Yeah, if we go back, we lost it. If we go back to the beginning of this here, we can see that there's a tight funnel here, right? It's just, they're so constrained. It's like maybe birds are chopping off this bit here, right? Maybe this is birds right here. That's just speculation, of course, right? But, Anders.
Yeah, so, a very interesting talk. So these very large dragonflies, if it was not oxygen that explained their existence, it seems to me that they started to die out in anticipation of
Oh, yes, okay, yeah. So hopefully I did not get too carried away with my dissing of oxygen. It's still believed that this part probably has a lot to do with oxygen. Yeah, yes. Yeah, you're in charge.
So, I've always been thinking about this. I think these large butterflies or damselflies are so cool, but we always see the pictures of the adults, of course. But what about the the dragonflies have this separation of habitats of their larval stage and their adult stage, and what about selection in the larval stage? How did this larvae look? What did they feed upon, and how has that diversity changed? You saw how other insects have also declined. Could it also be a bottom-up regulation that it could no longer be?
Yeah, I think
size?
that's also could be a very much the case because I mean the largest dragonfly that we have, it's living in Australia. It's like about the size of your hand. So you might be thinking, okay, like how long does that take to develop? It's just like the size of your hand. It's like, but they believe that this dragonfly has a development time based like somewhere around in decades. So 10 years to reach the size of a hand. That's a really long development time. I mean, if we compare it to like a mammal or something, right? That's absurd. So I think you're right. I think the larval stage is really important, and perhaps we should look more in, like, think about those constraints more than we actually do.
Now we have a coffee break.
Oh, okay,
Maybe
yeah.
there we can continue.
Okay. All right. Thank you very much.